morning, Nathan. I'm running late. It's 6 o'clock. I was supposed to be here an hour ago, but I overslept. So last set of notes for chapter 1. So you're coming up on the time where we're going to have a test, but we're going to have one more quiz. I think, let me make sure. Let me get my list of what all I do in this chapter. Yes, we're going to have a quiz on just section 1-4. So that was the angles. We'll probably do that tomorrow. That sounds like a good plan for tomorrow. And then we'll have a chapter 1 test. But you're getting close to having done everything. So yeah, I think chapter 1 is going well. You tell me though, and I know you will, because you will not just let it go by. Like, you tell me if there's anything we can improve. And if you have ideas how to improve it, just let me know, because I am all ears. And I just realized I've got the cover on my iPad right now. I don't know if it's covering up the microphone. I don't even know where the microphone is. So I should probably take that cover. Here we go. I took the cover off. I don't know if that helps. Tell me if it did. Tell me if it made a difference. Like if you can hear me better now than you could 2 minutes ago. All right, so section 1-5. This one's about postulates and theorems. And this is where the heart of geometry starts. Like this is the big stuff, okay? So we've already talked about a postulate. So postulates are, highlighters, no good. Statements accepted without proof. And I don't know if you know this or not. That is the shortcut way of saying without. That's the shortcut way, I guess shorthand's a better term, of saying within. So I will never write out the word without. Just in case you don't know it, that stands for without. So without proof. Ooh. Come on, there it goes. All right, so the two we've learned so far, let's see, we did the ruler postulate and the protractor postulate. Okay, so you've already taken notes on these. These are actually, like, they're super fundamental to everything we do. You know, this is what allows us to measure, segments. Okay, the protractor postulate is what allows us to measure angles. Okay. So yes, they're incredibly important. There's no good way to prove it. It's just like, oh, we can assign, here's 0, here's 1. That's the length of measurement. And then we can measure that anywhere we want. Same thing with angles. So we can say, oh, here's 0 degrees, and here's 180 degrees, and all these angles in between are 180th of that. And that's what allows us to measure angles. Those are the two you're not going to have to remember the name of, okay? These other three, they're the biggies. And we actually, now that I'm looking at them, I was like, we have actually talked about these before. So the segment addition postulate, that's where, all right, you take a segment. Let's say we call it segment AC. And you throw some point B in between there. Remember, if we use the word between in geometry, that means they have to be collinear. Then that means that the distance from A to B added to the distance from B to C is the same as the distance from A to C. And remember, you asked this yesterday, like, it matters the fact that there's not a bar above it. So like, let's see, let me pick, let's do green. Do I have a green one up there? I do. So if I said segment AB, then that would be segment AB. Like it's the actual geometric figure. So I like to think of it as like, if you're talking about the figure, there's going to be a figure in the name. So, the segment AB is the actual segment. This is just the length of that segment. So this is going to be a number. So it's going to be a number added to a number equals a number. You can't add segments. Like those are lengths. You can only add numbers. Okay? All right, so the angle addition postulate, we already talked about this, and you've used it doing some work. So let's say we got our big angle as angle ABC. And we're going to throw this ray BD in there that has the same vertex as angle ABC, and so it's going to be on the interior. Then we know that if we took the measure of angle ABD, so this one right here, and we added that measure to angle DBC's measure, that we would get the measure of angle ABC. So if you took the small angle, or one of the, remember, the adjacent angles. So if you take one of the adjacent angles measures, add it to the other adjacent angles measures, then you get that big measure that it encompasses. Now the same thing, this is a number, of course it'll be in degrees. This is a number. We can only add numbers. We can't add shapes. So we'll do this in green again. So if I actually just put angle ABD, then we'd be talking about the actual angle, not the measure of it. So that is really, 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 really important. And it's just going to take you a while to get used to it. It's just, I'm going to count off when you write it down wrong. And that's just, you know, it's not being mean. It's just we're going to be accurate. And then the linear pair postulate is a specific case of the angle addition postulate. So that's when you've got a straight angle. So we'll just draw a line. We'll pick a point to put in the middle. Well, I can't say middle because there is no middle. It's a line. So no way we can, somewhere on the line. And then, so we've got points A, B, C. They're all collinear. That means angle ABC is a straight angle. And then we're just going to throw a ray coming from B somewhere. And so if we look at this angle and this angle, and we take those two individual measures of those two individual adjacent angles, so the measure of angle ABD added to the measure of angle DBC, it still equals the measure of angle ABC, just like it did up here, but now we know what that measure is. And remember, one of the things that we can assume is if it looks like a straight line, it is. So, and I shouldn't have to say straight line because all lines are straight. You know, curve, line. A line is a type of curve. So don't go with what you learn in art because they call anything that you know, throw some writing on a paper, they're going to call it a line. It's got to be, the points have to be collinear for us to call it a line in geometry. And it is okay for you to assume that it is a line because otherwise the directions for all the problems would be just ridiculous. Okay, so you've got to commit the names of these three to memory. Like you just have to know, oh, that's that, that's that, that's that. You don't have to memorize this per se, but you have to understand it. So when we get to chapter 2, you'll see what I'm talking about. That's when we're going to start proofs, and I think you're really going to like proofs. But you're always going to be backing up what you say, and you have to have a reason to back it up. All right, so these next postulates, they don't have names. It's pretty much you just need to understand it. So a line contains at least two distinct points. Okay, so you got a point, another point, then that determines your line. A plane contains at least three distinct points, not all in one line. And I'm not real sure why I didn't just say non-collinear points. So you got, here's your plane. And then, okay, those 2 points are collinear because any two distinct points are collinear. You have to throw in a third point that's non-collinear. So remember, that's like the bottoms of the legs of a tripod to sit a camera on. That's why a tripod is shaped the way it is, because that determines the plane. It keeps it from wobbling. If we had tables with 3 legs where they didn't all line up, that table would never wobble. It's that fourth leg that's going to wobble, make the table wobble, okay? And then space contains at least 4 points. Oops, I guess I should put distinct here. It would be okay to actually leave the word distinct out because that's one of the things that, I don't remember which set of notes it was, where we just wrote like, we just understand that if we say 4 points, we mean 4 distinct ones. Like that's what's one of the things in geometry that people will say is assumable. Is that a word, assumable? But it's just habit. A lot of times I throw it in. So 4 distinct points, not all in one plane. All right, now to make sure that they're not all in one plane, here's how you got to do that. So you draw your plane. Okay, there's 2 points, collinear. That determines a line. Third distinct point that's not in that same line determines the plane. And then you've got to come through here and draw a line that's not in that plane and throw your 4th point on it. So like you have to know beyond the shadow of a doubt when you look at this picture that all 4 of those points are not in the same plane. Okay? And then postulate 6, these you don't have to know by memory. They just have to make sense. So through any 2 distinct points, there is exactly one line. And we already talked about that. 2 distinct points, there's the line that goes through them. And that's it. There's only that one. Okay? Through any 3 distinct points, there is at least one plane. Okay, now notice I said at least, because it just said 3 distinct points. So here's your 2 instances. Yes, it could just be in a single plane. If there are 3 non-collinear points, then that determines your plane. This one, there's only one plane that goes through, that they all lie in. However, if you took a line and you put all 3 points on the same line, there are infinitely many planes that go through that line. Like there's the plane the iPad screen, or we could come up off the ground with it, or we could tilt it a little, or like this part's gonna be hard for me to explain on a video because this is the part where I would take something flat and run it through those 3 points and go like, oh, tilt it a little more, tilt it a little more, tilt it a little more. So there's infinitely many planes that can go through that, okay? Through any 3 non-collinear distinct points, there is exactly one plane. And that's that one. Ooh, hang on. Too much orange and blue in the same place. Gross. Okay, there. You can't have orange and blue sitting together like that. All right, so postulate. If 2 distinct points are in a plane, then the line that contains the points is also in that plane. Okay, and I know I'm talking really fast because it's 6:12 now, and I've got to get this done and get it uploaded and do all the stuff. So I'm always going to talk fast on these videos. I mean, I know I talk fast in the first place, but it's okay on the videos because I know that you can pause it, you can slow down the speed, you can make me sound like this if you want to. So if you do slow down the speed, that would have sounded really, really funny. But, the fact that you can rewind and hear it as many times as you want, I'm not worried about talking too fast, But, so let's read what this says. If 2 distinct points are in a plane, okay, so if we're in a plane, we need to draw a plane. You put 2 distinct points in that plane. Then the line that contains those points, definitely in that plane. Okay, and people ask me all this all the time. They'll be, well, how do you show a point's not in a plane? You can't just go, okay, well, it's up here. Well, remember, planes don't have edges. Planes go on forever. I can't tell you for sure that point's not in that plane. It very well could be. But what I could do is put that point on a line that is most definitely not in that plane. That's how you show people that a point is not in a particular plane. I should probably get rid of that, though, because it doesn't go along with that postulate. Okay? All right, postulate 9. What color do I want now? If 2 distinct planes intersect, then their intersection is a line. Okay, so this is the one I always have to go back and erase because I have to draw my first plane. And then I'm going to draw another plane that intersects this. Oops, hang on. So I need to be running, I'm going to come down here and intersect it in this line. So I'm going to come up here. Now here's the aggravating part with this, because I do have to erase, because I'm not a very good drawer at all. Like, it's ridiculous how bad I am. Like, the part here that I'm about to erase is this little part right here, because I wouldn't be able to see that part. But when I erase, I connected all those. I have the stroke eraser on, because I think that's the best way for me to do this. Oops. So now I can see that part now. But any two planes that intersect, where they run together is going to form a line. Like look around the room. Let's say you take the front wall and the floor. Then where the intersection is that, I don't know, crease isn't the word, but the part where the floor hits the ceiling, or the floor hits the wall. So it's that line across the bottom of the front wall that's on the far front of the floor. It's like that's your line. And then there's a theorem that goes along with this. So now theorems we do have to prove, but oh, never mind. I was gonna say there's a theorem that goes along with this. I'm sitting here looking at my old notes because, you know, there's only so much time in the day. I'm not starting from scratch. But a theorem, we're going to get the definition of a theorem. So a theorem is an important statement that has to be proven or that can be proven. Like postulates, we don't need to prove those. They are just, there's no way to prove it. It's just basic to your understanding. A theorem, however, can be proven. Okay, so here's our first theorem. If two distinct lines intersect, then they intersect in exactly one point. Okay, so if you've got one line and the other, two distinct lines, that means there's 2 points here, there's another point there. That means these lines are all in the same plane. There's that one point where they're going to intersect because that's just the shape of a line. And I really just did a lousy job right there of saying that I can prove this because to me this one's almost a postulate. Off the top of my head, I really don't remember how you prove this because in my opinion this was just understandable. But so that was a really lousy job to start out with. Okay, theorems, you can prove them. And here's one that I'm not going to prove. So I'm going to think on that again because I just realized I'm not really sure exactly how you prove that. Let's see. It's got to be based on the postulates we just wrote down, so let's think about it. So you know that you'd have the one plane they're in, so they can only intersect in that one point. So which of these postulates leads us there? And again, like I said, I think this one, like to me, this is a postulate. But according to the math book, it's a theorem. So how did they prove it? I could just, hang on. I'll look it up. I've got the math book right here. Oh. So theorem 1-1, how did they say to prove it? I may just read you what they said. Of course, you've got the book too, so you could look it up. It's on page, let me find it. Theorem 1-1. Oh, you know what it says in here? It says that, here's what it says about, there's going to be 3 theorems right here. Theorem 1-1, 1-2, and 1-3. Important statements that are proved are called theorems. In classroom exercise 1, you will see how theorem 1-1 follows from the postulates. Okay, so that's on page 23. So then they flip over here to the classroom exercise. And here they're going to walk us through it. Theorem 1-1 states that the 2 lines intersect in exactly one point. The diagram suggests, so this is over on page 24. So you can pause this and get out the PDF or the textbook, or you can just come back here and borrow my book if you want to have it in front of you. The diagram suggests what would happen if you tried to show 2 lines drawn through 2 points. State the postulate that makes this situation possible. Okay, so what they're saying is, let's say you had 2 lines that went through that intersected in 2 points. The only way that would happen is if they weren't actually lines. So they're saying the postulate that says that's true is that through any 2 points, there is exactly one line. So if you had, that's where they're getting it. So they're like, okay, if you have 2 distinct points, there's only the one line that can go through it. So if we have two distinct lines, you have to have more than two distinct points because of postulate. Where is it? Right there. Through any two distinct points, there's exactly one line. Okay, but again, this is not really the theorems and postulates that you have to remember are the ones with names. Okay, the other ones you just have to understand. And then, oh, this is really, really, really important. What's the difference between one and exactly one? Okay, exactly one is exactly what it sounds like. There's exactly one. I have exactly one brother, because that's true. I have exactly one brother. However, my mom can say, I have one brother, but she also has two more. So when you just say in geometry or math in general, if you just say one, that means at least one. But when you say exactly one, it means exactly one. So kind of important. All right. So theorem 1, 2, through a line, which has two distinct points on it, and a point not on the line, there is exactly one plane. Oh, I did the orange and blue again. Hang on. Oh, okay. I don't know if you're a football fan or not, Ethan. I'm not. I don't like orange and blue because I'm an Alabama fan and I don't want Auburn colors. So if there's your plane through a line and a point not on the line, there's exactly one plane because it goes back to, where is it? Through any three distinct points, there's at least one plane. But it's exactly one plane because you throw in that non-collinear one. Oh, this picture. Okay? All right, and then the last one, if two distinct lines intersect, then exactly one plane contains the lines. Okay, so if two lines intersect, well, that means you've got two distinct points on this line. You've got two distinct points on this line. These, let's say we pick that point, that point, and that point. There's your three non-collinear points, and therefore they're all in just one plane. So it goes back to those postulates above that didn't have names. Like, you don't have to know it's postulate 8, postulate 9. Again, you just have to understand it. Okay? All right, let's see if we can make a video. I think we can. Do you know what one of the big problems, there were many problems the other day, but do you know what the biggest problem was? And I'm embarrassed that I have to admit this and that I didn't notice it. Somehow or another, this computer, this iPad, I guess you'd call it a computer, it's just an iPad. So it was in airplane mode. Video's not gonna upload very well in airplane mode. Don't know how it got there. Not real sure how I managed to turn that on, but Mr. Anderson, like we worked and worked and worked, and finally he goes, wait, there's a little airplane at the top of the screen. Oh, dadgummit. Okay, so let's see if I can get this going.